In 2023, Anthropic showed you could pull clean, interpretable features out of a tiny one-layer language model using a technique called a sparse autoencoder. Beautiful. But the obvious objection was, sure, on a toy. Will any of this survive contact with a real, deployed frontier model, with billions of parameters and genuine intelligence? This paper, Scaling Monosemanticity, is the answer. They took those same tools all the way up to Claude 3 Sonnet, a production model, and asked, can we actually read the concepts inside its mind? The answer turned out to be a resounding yes. A quick reminder of the problem. If you look at a single neuron inside a language model and ask what it represents, you usually get nonsense, because neurons are polysemantic. Each one fires for a grab bag of unrelated things. That's superposition. The model packs far more concepts than it has neurons. A sparse autoencoder fixes this by re-expressing the model's activations in a much larger but sparsely active set of new units, called features, each one tuned, ideally, to a single concept. Monosemantic features instead of polysemantic neurons. That's the whole game. And it's scaled. Training these sparse autoencoders on Claude 3 Sonnet, the team extracted vast numbers of features, and the more capacity you give the dictionary, the more distinct features you find, smoothly, predictably, into the millions. There's even a satisfying phenomenon called feature splitting, where a single coarse feature in a small dictionary, say a generic bird feature, splits into many fine-grained ones, specific species, as the dictionary grows. The resolution of the microscope improves as you scale it. And these weren't shallow, surface-level features. Many are strikingly abstract. A single feature might fire for a concept across completely different languages, the same idea in English, Russian, and Japanese, and even across modalities, activating both on text about a thing and on images of it. The feature isn't tracking a word or a pixel pattern, it's tracking a concept, the way you'd hope a genuine internal representation would. That abstraction is what makes them so useful to read. Crucially, the features are specific. When you look at where a given feature fires across a huge amount of text, it switches on strongly for its concept and stays quiet for almost everything else. That sharp selectivity is what lets us actually name them. This is the feature for the Golden Gate Bridge. This is the feature for a particular kind of code error. Without that specificity, the features would be just as muddy as the neurons we started with. Even better, the features are organized. If you lay them out by similarity, related features sit near each other, forming neighborhoods. Around the feature for the Golden Gate Bridge, you'll find features for Alcatraz, for San Francisco, for other landmarks and tourist sites. It's effectively an atlas of the concepts the model knows, with related ideas clustered into regions. You can wander this map and watch the model's mental geography unfold. Zoom out and the structure is genuinely beautiful. Thousands of features arranged into a sprawling conceptual landscape, with continents for science, for emotion, for code, for places. This is the kind of picture interpretability researchers had dreamed about, not a black box, but a navigable map of what a frontier model has learned. And remember, this is a real production assistant, the same kind of model people use every day. Let's make it concrete with the feature that became famous. There's a feature that fires whenever the Golden Gate Bridge is relevant, in text describing it, in mentions of crossing it, and even when shown a photo of it. It is, as cleanly as you could ask, the model's internal concept of that one bridge. On its own, that's a lovely demonstration that the features are real, but the team did something far more striking with it. Here's the pivotal point. These features aren't just passive labels we read off the activations, they actively drive the model's behavior. You can prove it by clamping, artificially forcing a feature to a high value, while the model runs and watching what happens to its outputs. If the behavior changes in a way that matches the feature's meaning, then the feature isn't a correlation, it's a cause. So they grabbed the Golden Gate feature and turned it way up. The result was Golden Gate Claude, and it was both hilarious and profound. With that one feature clamped high, Claude became utterly obsessed with the Golden Gate Bridge. Ask it for a cookie recipe, it relates the ingredients to the bridge. Ask who it is, it starts to identify as the bridge. A single feature, out of millions, reliably and dramatically steered the entire personality of a frontier model. That's about as direct a demonstration of causal, interpretable structure as you could possibly want. As fun as Golden Gate Claude is, the real motivation here is safety. If a model represents concepts as fundable, steerable features, then in principle, we could locate the features for dangerous or deceptive behavior, monitor when they fire, and even turn them down. So the team went looking, on purpose, for safety-relevant features. What they found is sobering and important. They found features for a whole catalog of concerning concepts, features for security vulnerabilities and backdoors in code, features for bias and slurs, features for deception, for psychophancy, for power-seeking and grandiosity, features tied to dangerous technical know-how, like bioweapons. There's even a feature that activates around secrecy and hidden agendas. The model clearly represents these ideas internally, and now, for the first time at this scale, we can point to where. And these safety features are causal too. Clamp the deception feature or a scam email feature, and the model's behavior shifts toward that, just like Golden Gate Claude. That cuts both ways, and the authors are clear about it. The very same tool that lets us detect when a model is being deceptive or drifting towards something harmful could also be used to induce that behavior. Interpretability of this kind is genuinely dual use, a window into the model and a lever on it at once. Looking at where these features fire is itself revealing. The code vulnerability feature lights up precisely on the buggy or exploitable lines. The bias features activate on exactly the prejudiced content. Because the features are specific, they act like detectors. You can run them over text and see, token by token, where the worrying concept is active inside the model. That's a fundamentally new kind of visibility into what a model is thinking as it writes. The team is careful not to oversell it, and the limits matter. The sparse autoencoder is incomplete. It captures many features but certainly misses a great deal. There's a lot of unexplained dark matter left over. The features aren't perfectly clean, some are still a bit mixed. Training these dictionaries is computationally expensive, and this is a single snapshot of one model. So this is a real microscope, but one with genuine resolution limits, not an X-ray of the entire mind. Still, the significance is hard to overstate. Before this, a skeptic could argue that dictionary learning was a cute trick that only worked on toy models. After it, we knew that the same approach scales to a real, deployed frontier model and recovers millions of genuine, human-understandable concepts, specific, abstract, multimodal, and causally active. This result is the bedrock that the later attribution graph and biology work was built on. You need a good set of features before you can trace circuits between them. So, can we read a production AI's mind? To a real and growing degree, yes. Inside Claude 3 Sonnet are millions of interpretable features, the model's concepts laid out in a navigable map. They're specific enough to name, abstract enough to span languages and images, and, most importantly, causal, clamp one, and the model's behavior follows, including, soberingly, features for deception and danger. We now have a microscope that works on frontier models, and the task ahead is learning to use it well, to make these systems more transparent and safer.